The world is informationally very rich, and even richer in an environment with a live agent. The question is, how the human brain compute all this information and give us the correct information about the world, while whether the perception that we have about the world is veridical is questionable. It is certainly sure that our brain is able to form reliable representation of the world, enabling us to interact with each other seamlessly. A veridical perception is the perfect description of the world. E.g., if our brain is giving us the veridical perception, then we are perceiving the world as it is. But if our brain is not giving us the veridical perception, then it is essentially creating a world of its own, and that is what we are perceiving. Why does this matter? If it were to be a veridical perception, the brain must compute all the information in the world in a principled way so that everything it represents corresponds to the world. But given the complexity of the information in the world and the constraints that's put into the neural systems, it doesn't seem very plausible. What's more plausible is the brain reduces the complexity, i.e. the dimensionality, and generates simplified but very accurate representation of the world. If we come to think of it, our brain is essentially in a vat, isolated from everything in the world, and the way it uses to construct its inner representation of the world is to use simple electrical signals. Though the property of electricity might be simple, the computations that follow the signals are never quite simple. What kind of computation the brain would do? One of the interesting theories of brain's computation is that what neurons do is the Fourier transformation, which is the mathematical relationship that models the flow of energy between two different domains. For example, much information is composed of the frequency, and the brain gets this information using the intricate structure of the neurons, and then through complex interaction of neurons in the brain, the energy is decomposed and transformed into another form, which gives rise to the perception and/or consciousness. For example, we know that our brain is very good at edge detection. But the astounding question to be answered is how the brain knows the identity or the category of the objects. I now see a cat, and I can tell where the edges are and so on, the physical descriptions of the cat. And what I wonder is how the cat's information is stored in my brain that's so reliable and stable that whenever I see a new cat of the same kind, I can clearly say that's an animal that belongs to a category called a cat. Or even more interesting is detecting faces. When I see a face, it's no wonder that I know where the eyes are, where the nose is, and so on. What's really puzzling is how the brain differentiates different faces in a meticulous detail every single time. How it's represented. If the computation is implemented based on the sets of functions that can reduce the dimensionality of the world in a principled way, the world might be represented in a very principled manner. And one of the candidate ideas for these sets of functions is that they are guided by the rules of second-order isomorphism. What is second-order isomorphism? In mathematics, an isomorphism is a structure-preserving mapping between two structures of the same type that can be reversed by an inverse mapping. And the second-order isomorphism in terms of the brain's representation is the isomorphism between the similarities among shapes and the similarities among representations that they induce. Then, why second-order isomorphism? First off, it's computationally very conducive. If the representation were to be based on geometric shapes, the amount of information that the brain needs to store is insurmountable, let alone the computation that it does every single time. On top of that, the representation based on geometric shape cannot explain our ability to learn novel stimuli. But if the representation were to be based on the second-order isomorphism, the ability to learn novel stimuli can be easily explained, let alone the computation ability. What could be the mechanism for that? Here's one example. Let M be a mapping that's implemented by a typical visual system, then such a mapping can be described generically as a composition of four functions. The following is the rough schematic description of mapping M. The first function is about the geometry. Let P be a set of parameters that describes the world, which could be, say, quantum field's wave function. Then function f1 maps P of the object into its geometry, which might be composed of vertices, edges, and so on. Then the second function f2 maps the object's geometry into the image on the receptor surface of visual system, which in our case, an image of an object that's formed in our retina. And this process involves extraneous factor z, which includes pose, illumination, etc. Then the third function f3 corresponds to the set of internal measurements performed on the image, which in our case, some kind of a computation that is performed by optic nerve and visual cortex that extracts some information of the image, such as the edges, colors, and so on. To ensure as many possible variations among the objects along the original dimensions are preserved, it's worthwhile to make as many varied measurements as possible. This makes measurement space f3 high dimensional and then necessitates subsequent dimensionality reduction through the action of f4. Finally, the last function f4 maps the measurement space into a low-dimensional representation while removing the dependence on the viewing condition z. For this scheme to work, it is required that the variable z's influence on the perception must be counteracted by the perceptual system through the combined action of f3 and f4. Then, the mapping M will result in the brain's representation of the objects. Note that the axes in brain's representation have apostrophes with them to indicate that they are derivatives of the original axis. The arrows indicate the distances between the representations. If those distances, i.e. similarities, between the representations are preserved, then this becomes the second-order isomorphism. This way of viewing the representation of the brain wasn't very new. For example, David Marr wrote a book about the vision in 1982, whose idea was heavily used in developing neural networks, especially deep convolutional neural networks. Nowadays, a representational similarity analysis, one of the robust brain data analysis techniques, also sheds light on how the brain works by analyzing the representation of the brain as the target of the analysis. One interesting result found using the representational similarity analysis is that brain's representation of the visual input is similar to that of convolutional deep neural networks. As our understanding about the brain gets better, our ability to make a use of that gets better as well. It's not only helping us to make a better use of it, but also to see the world with a better lens. What constitutes the world and how the brain does its job will not be solved anytime soon, but the attempt to understand the brain should continue.